All right. Give me 1 second. I think I actually have to change my sound settings. Okay. Sorry about the delay. Okay, so before we start, I'll just quickly say regarding the projects, everyone should have received a feedback about your project abstracts as well as your grade. So if you haven't received that, please let me know and I can send that over to you. For the most part, the abstracts look pretty good, and most of the feedback is just helping to provide a little bit of direction for working on the outline and the final report. Regarding the outline, I did make a short little guideline for everyone. I posted that on Canvas, so have a look and sort of follow that for when turning it in. And just as a reminder, we push back the due date, so it's not due on Wednesday. It'll be due on May 20th, which is the Wednesday of next week. And then lastly, I was able to get some examples of previous projects and presentations. So you can have a look at those. They're also posted on Canvas. Okay, great. So today we'll be talking about transportation and alternative fuel vehicles. This is a topic that is near and dear to my heart. Most of the work that I do is actually in transportation energy. And so I've been working in this area for about a decade now. And it's pretty important. So when we're thinking about energy consumption and thinking about climate change and emissions impacts, transportation itself uses about 2/3 of primary energy use and GHG emissions, and quite a large fraction of air pollutant emissions. And so this is definitely one of the most impactful sectors when we're thinking about how to address issues with climate change. The vast majority of transportation, right, if we think about cars, buses, trains, boats, airplanes, they basically all depend on oil. 97% depend on oil. We will talk about some of the up and coming technologies, and I'm sure lots of you guys are familiar with or maybe have even ridden or driven in something like an electric vehicle. But at the end of the day, it's still a pretty rare technology relative to our status quo. One of the big issues is that at the same time that we're trying to decarbonize transportation, the third world countries and developing populations are starting to get more and more access to transportation. And so actually the total number of vehicles is projected to triple by 2050. And that poses a lot of sort of interesting questions as well. And we've talked a little bit about this, right? About the dichotomy between pushing for clean climate. So from like an electricity standpoint, you would want most new energy to be, say, from renewables and to be clean. On the other hand, you don't want to stifle developing countries from having access to electricity. And so maybe they're building like coal plants in certain developing areas. And it can be a difficult struggle to balance between getting electricity and energy in the cheapest way possible to people who need it versus trying to make it clean so that our climate can be better. And so it's the same thing here, right? Maybe we would want all new transportation development to be clean and sustainable, but you're sort of balancing against the needs of those who just don't even have access to it. So that's an important point to think about that we probably won't talk about too much more in this lecture. Over worldwide, about 20% of greenhouse gases are coming from transportation. 28% of US GHG emissions, 40% in California. So the reason why it's so much higher, relatively speaking, in California is actually because the electricity system is already really clean. And so transportation ends up taking sort of a bigger slice of the pie. It's also one of the few greenhouse gas sources that is continuously and rapidly growing, despite things like improvements in efficiency. So when we think about improving energy use, improving emissions, there's basically 3 different ways we can do this, right? And so transportation efficiency, so that is for every sort of unit of energy that I put in, I'm getting more sort of useful output out of it. So these are things like vehicle fuel economy, and that's kind of the one that most people think about when it comes to transportation efficiency. But there's actually a couple important other ones. So congestion relief. This is essentially independent of the vehicle itself. You can imagine that if you are in stop and go traffic, constantly going at different speeds and slowing down, losing a lot of energy to braking, that's extremely inefficient. And so if you could actually design your cities and your land use and infrastructure in a way to avoid congestion, that you get a lot of benefits in terms of efficiency. Road design can be a factor, right? So the way that your vehicle, for example, even the friction between the road and your tires, that has some effect on efficiency of your transportation mode. And then lastly, intelligent transportation systems. We won't talk about this too much today, but if you think about future vehicle technologies such as automation, this is one where you can really take advantage of being able to do things like platooning, which is when a whole line of cars basically follow each other very closely. It reduces air resistance, and the cars behind the front car get a lot more fuel efficient. You can get up to 30% more fuel efficient from doing something like platooning. Um, yeah, if anyone ever watches like uh, cycling races, people will get in these straight lines to reduce air resistance. It's the same principle. And if you had vehicles that could communicate with each other through autonomy and connectivity, you could replicate that sort of thing. So these are all points under the transportation efficiency column. And then the next one, which we'll spend most of our time today talking about, is actually just switching to alternative fuels and different vehicle technologies. So these include hydrogen, biofuels, electric vehicles, and then you've got advanced ICE engines, which sometimes people would consider falling under transportation efficiency, depending on exactly what the technology and configuration is, and then other low carbon liquid fuels. And then the last one is more of a behavioral change. I personally am not super optimistic about this, because I think that individuals' preferences and behavior is probably the hardest thing to change, rather than just um, inventing and innovating on new technology. But it is a really, really important topic, and there are a lot of folks working really hard on issues related to behavior. And so, one of the ways, someone once asked me, what's the best way you can double the fuel efficiency of a vehicle? It's actually pretty simple. You just get everyone to go from one person per car to two people per car. Right now, you're carrying twice the load. You need half the number of vehicles and miles traveled. So carpooling can really make a huge difference. Then on a marginal basis, compared to something like fuel efficiency, right? We have all this regulation, and we struggle really hard to improve the vehicle technology and efficiency, and you're talking about something on the order of like a 20% improvement over the next decade or so. Whereas with something like with carpooling, you could literally double the efficiency with fairly low effort in the technology realm. You just have to change people's minds. So in the same vein, mass transit and also urban design that would help shift people from one mode to another. So if you could, for example, forego a car trip and make someone do a bike trip instead, you can imagine how much energy and emissions you're reducing. So again, I think these are extremely effective methods as it relates to behavior, but I think it's also probably one of the hardest to change. I should mention, from a policy perspective, that California has legislation and regulation across all of these categories. And unfortunately, I think the one that has been the least successful is reducing VMT or VKT. In other words, trying to change people's behavior. If folks are interested in that, you can look to, there's a Senate bill called SB 375, which is focused really on the behavioral aspect. And there's a lot of research done on that, even here at Davis, about the impacts of that and whether or not the regulation has been successful. Okay, so this is what I was just discussing. These are sort of the technical options. So mainly in the first two categories for sustainable transportation. So we'll think about some of the status and projections as it relates to each of these things. So for travel demand reduction, these are, as I was mentioning, policies to encourage things like mode switching, so carpooling, cycling, walking, combining trips, or even telecommuting. And that's a big one, especially these days, right? So no one is, unless you're doing essential work, you are most likely telecommuting. And that's actually led to some pretty dramatic decreases in the use of our transportation system and the associated energy and greenhouse gas emissions impacts. And so one of the things that that folks advocate for are policies that promote what's known as smart growth. And so if you plan cities in such a way that you don't have to travel as far, or you design the city to be more accommodating for, say, walking and biking as opposed to driving, it inherently gets people to switch to other modes. And so, you know, the sort of more well-traveled among you may have gone to cities before, especially, for example, in Europe, where there's a big emphasis, for example, on biking infrastructure or on commuter rail lines. And so getting around is not only sort of designed to promote those, but it's a lot easier, right, to be commuting via a tram rather than sort of sitting in traffic. Whereas a lot of American cities, bigger American cities, it would be basically impossible to get around without a car. You just don't even have the option. And so those types of policies and practices are not necessarily the first thing that a lot of folks think about when we say improving our transportation system. A lot of folks sort of latch onto getting to new technologies, but this is a good way of addressing this travel demand aspect of it. So higher transport system efficiency, shifting to more energy efficient modes of transportation. And so this is shifting modes to things like mass transit. So if you use bus or rail, right? So an individual bus is a lot less efficient than a car, but most cars only have one passenger. I think something like in the last survey that I saw, over 90% of vehicles on the road basically just had a driver and no one else. And if you put all those folks into a bus, then you end up getting a per passenger efficiency that's quite a bit higher than for cars. Okay. And then the last one is thinking about potential for alternative fuels. So we've talked about how switching from gasoline to an alternative source helps with a couple topics. So, even if you don't believe in climate change, which hopefully no one in this class is on that bandwagon, even then, oil supply security, national security, security for your energy resource is one sort of really big benefit that's really sort of independent from issues with climate change. And so there are benefits to be seen across a variety of different topics. Some of the alternative fuels that we'll be thinking about, biofuels, electricity, hydrogen, We're not going to talk so much about advanced fossil-based fuels. So this is like unconventional oils. We have discussed this a little bit um, in previous lectures, but these are like synthetic fuels. So if you were to make gasoline not from oil, but through chemical processes, the generation of that fuel, if it's done with a renewable resource or something like CCS, it could, in theory, be clean. And to give some kind of perspective about the sort of potential in the future for alternative fuels, this is a diagram of pathways for our fuels today, right? We basically have oil, we have some unconventional oil, it gets refined into gasoline and diesel, and then it gets used in, so I should note the abbreviations here. There's lots of acronyms in transportation, so um, I'll go over them as I see them, but if I miss one, feel free to speak up. So ICEV, so this stands for internal combustion engine vehicle. So we call basically conventional vehicles ICE vehicles, and then HEV stands for hybrid electric vehicle, and that is something like a Prius. It still uses gasoline, but it has a battery that lets it do, regenerative braking and such. There's a little bit of natural gas that can be used in internal combustion engine vehicles. There are certain types of natural gas combustion vehicles. They're pretty rare, but they do exist. And then we have ethanol coming from biomass. And so those are both blended into gasoline for regular cars, but also in flex fuel vehicles. Okay. And then when we think about potential futures, we'll talk about these technologies in just a second. That you've got your plug-in electric vehicle, a full battery electric vehicle, and a fuel cell electric vehicle. And the potential energy sources in which you can essentially make any of these alternative fuel vehicles is coming from a huge variety of sources. And so you probably want to avoid, the more fossil fuel based ones, and you want to transition to these renewable sources. But the point is, these technologies are offering lots of potential pathways into the future. So this is a little bit of an older graph. I couldn't find an update for this. Global transportation energy consumption by mode. I will say that it's pretty unlikely that these breakdowns have changed all that significantly in the last 8 years. Maybe for some of the developing countries, it would have changed, or countries that are going large developments. So things like China and India may be a little bit different as their passenger vehicle fleet continues to grow rapidly. But you can see in the vast majority of countries, most of the energy is going towards on-road passenger. And so these are just, the regular passenger cars that you see every day. And then there's a substantial amount of freight. And the combination of marine, air, and rail are relatively small compared to the other two, but still represents a non-insignificant portion of the total. Again, this one is a little bit older, but one that probably hasn't changed very much either. You can see in each of the countries, the fuel breakdown of their transportation system or their transportation sector. And the combination of the blue and purple usually accounts for something like 2/3 to 3/4 of the total energy use. And those colors represent purple for gasoline and blue for diesel, so mostly oil. The remaining components are um, basically comprised of jet fuel and heavy fuel oil. So jet fuel is for aviation, obviously, and heavy fuel oil is typically used in ships. And so you can see that when it comes down to fossil fuels, that is the vast majority of energy use in the transportation sector. Okay, and I see a question: is the electricity on the figure all from the listed energy? I'm not sure what you mean. Oh, okay. So why do we sort electricity with others together? So that's actually because of electric drivetrains. So electric vehicles, for example, would use electricity. So we include that. So this is kind of the endpoint in the actual transportation technology. And it's a really small sliver right now. Especially in 2007, it's grown really quite rapidly over the last decade, and we'll be able to see some of that coming up. Okay, I'm gonna just skip that slide. Let's move on to here. So as we begin to talk about some of these future technologies.
And there's another question about
that. Yes, okay, I see. Eric has a question: why does Europe use much more diesel than North America? Yeah, so there are a couple historical reasons for that. The diesel and gasoline, when it comes down to technologies that use them, have slightly different implications in how they're used. So diesel tends to run more efficiently at higher speeds and provides more, let's see, I guess the power density that you get out of it is what you would need for things like freight. And the other thing is that when you have stricter requirements for pollution outcomes, it can be harder to use diesel systems because they're typically going to have higher proportions of air particulates such as NOx. And so Europe is, I think, a little bit more lax in that regard, so it's easier to use diesel. But it's a combination of factors. I think it has to do with basically the fact that, or was it sort of building off of status quo. I think diesel is just more widely accepted in Europe than in North America. Yeah, I'm not sure exactly the historical reasons for why there exists more diesel, but it's sort of continued on that way. I will say one of the contributing factors is that the fuel prices are also really high in Europe because they have much higher taxes. And so there's sort of a stronger incentive for efficiency, which you can tend to get with diesel, but you're making sort of a trade-off, like I was mentioning, with the pollution. Yeah, so there's a number of different factors and reasons as to why you have this difference in composition. Okay. So the rest of the lecture, we're going to cover basically two of the newer alternative fuel vehicle technologies. And as we think about these, the adoption of new vehicles tends to follow this sort of process. And so, don't worry too much about the exact numbers and how these sort of line up as on the y-axis. This is more sort of telling the story about the process with which new technologies get sort of penetrated. And I should also mention that I mean, this in itself is a fairly big field. You could actually take some classes specifically related to kind of this diagram right here. And so this isn't actually just unique to vehicle technologies. This is applicable to essentially any new technology. So cell phones, I think refrigerators, this was a sort of classic example of. But essentially, the way that you get from early stage, right, in a lab up to commercialization and sort of widespread deployment, you go along these sort of different phases. So you got your R&D, product development, pre-commercial sales, early commercialization. And so these curves are called adoption curves or diffusion of innovation curves. And there are actually a whole other set of components sort of as you move farther and farther along your total market penetration. And there are also pretty interesting aspects of this where you think about, who are the types of people who would adopt the technology first? So people who are typically, but not always, higher income, maybe more open-minded about new technologies or sort of follow the newest technological trends. More recently, folks have begun to characterize early adopters as also for certain types of technologies, people who care a lot about the environment or climate change. And so, as I was mentioning, it can be a fairly big field in and of itself to try and understand sort of different components of the market. So thinking about, who are all the people down here that are buying cars? How can we translate that to, a more mainstream market of people in this portion of the curve? Like how can you improve the technology? How can you pass policies that will sort of push you along this curve? Okay, so let's go ahead and start off and talk about electric vehicle technology. The different types of electric vehicles, sort of to clear up the nomenclature here. I did talk briefly before about HEVs, which are hybrid electric vehicles, things like a Toyota Prius. And that often gets confused because hybrid electric vehicles have the word electric in them. So people don't realize that, they're not electric vehicles in the sort of full sense of the word. You don't plug them in. And importantly, oftentimes the sort of distinguishing factor is that the drivetrain of the vehicle can operate entirely at some point on just the battery. That's actually not a great distinguishing point anymore, because actually a lot of even hybrid electric vehicles have batteries that are large enough where they can go like really short distances and in slow speeds without turning the engine on. So like it's the newest models of a Toyota Prius, you could go, I think something like half a mile to a mile, um, if you're going below, I think 30 miles per hour without actually turning the engine on, if you have the settings correct. So even that starts to get a little bit confusing, and so these days the way I like to explain it to folks is that we consider electric vehicles to be vehicles that plug in. And so that you've got your battery electric vehicles, BEVs, which are commonly known as vehicles that operate entirely on electricity and it only has a battery. So examples of this include like the Nissan Leaf, the Tesla Model S, the Tesla Model 3. Those are all full battery electric vehicles. The other sort of flavor of this is a plug-in hybrid. And a plug-in hybrid is a vehicle that has both a gas engine and a battery. And most of the plug-in hybrids these days, they're all have slightly different flavors, but the way that I again like to sort of describe these is that you have a battery that's smaller than a full battery electric vehicle, and for the larger plug-in hybrids, you're usually getting around 40 to 50 miles. So things like a Chevy Volt or the Honda Clarity plug-in hybrid, those will have 40 to 50 miles. You drive on the battery, and once it runs out, the engine will turn on, and then you can drive on an engine. So you actually might think to yourself, well, 40, 50 mile range, that seems like really small, and that you're just going to be using the engine most of the time. But you have to remember that actually the vast majority of trips are actually going to be much smaller than the range of the vehicle. So in the US, I think about 87 to 90% of trips by passenger car, are less than 25 miles, which means that you could actually go, if you think about trips that are being made every day, you go to your destination and back home for less than the range of the vehicle. And then when you really need to go a long distance, well, then you can use your gas engine, but it's not like you're driving to, Yosemite every day. So actually, even though the range of the vehicle is may be smaller compared to a full battery electric vehicle, you may be getting the same amount of electric miles out of it compared to a battery electric vehicle. And in fact, there is some research that we do here about people's behaviors and preferences and how they drive the vehicles. And in some cases, you can actually get more electric miles out of a plug-in hybrid than you could with a battery electric vehicle. And one for example, one reason you could see that happening is if in an actual household where you have two vehicles, we actually observe that you'll take the plug-in hybrid more often, and then in the longer trips, you might substitute to sort of a larger, less fuel efficient vehicle if you're driving a battery electric vehicle, because it couldn't actually make the trip all the way down to LA, for example. And so that is a trip that you would do with a plug-in hybrid, but maybe not with a battery electric vehicle. So there are these weird sort of interactions with other vehicles that you own that could lead to these pretty interesting substitution behavior between your BEVs and your plug-in hybrids. Okay, And then the last one, which we'll talk a little bit more about today, are fuel cell vehicles. So these are technically electric vehicles because they convert the power to electricity and to power a motor. And so, yeah, again, we'll talk about this a little bit more, and we'll show some examples of this. So electric vehicles, probably the first electric vehicle of the modern era, some folks may be surprised to know, is that was actually happening in the 90s. And so that EV, in 1990, there was this regulation that sort of pushed automakers to start producing electric vehicles. And General Motors unveiled their EV1, which is this top left picture, beginning in 1996. But that was shortly discontinued afterwards. A lot of people talk about self-sabotage. So there's a pretty fascinating documentary. If you guys find yourself bored at home and you want to take a look, it's called Who Killed the Electric Car? And there's actually a follow-up documentary called Revenge of the Electric Car, which is sort of addressing a follow-up of the first documentary. But anyways, that electric vehicle had a lead acid battery, an 18.7 kilowatt hour battery, which translates to about 80 to 100 miles. And then later, in later generations of it, before it was canceled, they upgraded it to a nickel metal hydride battery, an NMH battery, which coincidentally is the sort of battery that's really mainstream in hybrid vehicles before they started switching to lithium batteries. I'll quickly mention that yeah, even though this date is in the 90s, so you might think that gas cars have been around a lot longer than electric cars. Actually, electric cars preceded gas cars by quite a bit. It wasn't until the late 1890s, I believe, that you had your first gas car. But electric vehicles had been around since I think the early 1800s or mid 1800s. Depending on the variety that you're talking about. But I think really the first kind of commercial product that's available to consumers to a slightly wider scale, you've got your 2008 Tesla Roadster, and then Fisker Karma at the beginning of 2011. But I would say they're not exactly sort of mass market vehicles. The first vehicles, so this is the Tesla Roadster on the left and the Fisker Karma. The first, I think, really mainstream commercial product is the Chevy Volt and the Nissan Leaf, both of which were released in the end of 2010 or beginning of 2011. And so I think that's really where all of this has started. To give you a sense of scale for the number of vehicles being sold every month and the different available vehicle models, I think this is kind of surprising to a lot of people. There's probably around 40 to 50 different electric vehicle models that are just available to purchase these days. And you can see here how that's grown pretty rapidly over time, beginning right down here, blue and red for your Chevy Volt and your Nissan Leaf. One of the other sort of big popular ones is the Tesla Model S in green. And then I don't think they have, let's see, the Tesla Model 3 on here. Yeah, I think this is a little bit early. I haven't updated this graph, but since the Model 3 has come out, it has dominated basically all electric vehicle sales. And so the Tesla Model 3 outsells all other electric vehicles in this list combined by a lot. And so there's some worry by some analysts about whether or not that's kind of sustainable and whether it's, hurting the um, competition and being able to develop and popularize their other vehicles. But I don't know, at the end of the day, I think any electric vehicle sales are going to be pushing the technology and the market forward. So I think it's a good thing. And just to give some perspective, so there's a question, what's the number on the y-axis? Sorry, this is number of sales. And so in a given month, you're talking about tens of thousands of vehicles being sold. What was I going to say? Oh yeah, so in California, to give some perspective, we are up to about 10% of sales of new vehicles being sold are electric, which is great, but we also still kind of have a ways to go before we are able to integrate the new technology as sort of mainstream. And not only that, even if you were to get to 100% of new vehicle sales being electric, if that happened overnight tomorrow, it would still take 10 to 15 years for all the vehicles to turn over in our existing fleet, right? And so, people don't go out and buy a new car every year. You hold on to your car on average something like 10 to 12 years. And that belies some of the difficulty in meeting some of our climate goals. So if you go back and you look closely at the targets and what would be needed to accomplish that, the electrification of transportation, we're actually working on a big project with the California EPA to think about how we might totally decarbonize all of the California's energy system and transportation by 2045. Well, so if we were to do that and we were to give, a 15-year lead time to completely electrify all new vehicle sales, right, because of the time it takes to turn over existing vehicles in the fleet, then you would need to get to 100% by something like 2030 to 2035. And so we've gone from 2010 to 2020 from 0% electrics up to about 10% just in California. And from there, we need to go from 10% to 100% in another 10 years. So it's still a really difficult problem. And in terms of projections, I'm not going to pretend to be a prophet, even though a lot of my work does stuff like this. A lot of people think that they can predict what the adoption of electric vehicles are going to be, but everyone's coming up with different numbers, and so we'll see, right? There's definitely a need for a lot of this stuff, but there's a lot of uncertainty. Right, you never know when the next big pandemic is around the corner, and we've actually been tracking vehicle sales and electric vehicle sales over the last month or two, and vehicle sales have essentially plummeted. Not a lot of people are buying cars these days, and so that may hinder some of the work that's gone into pushing this technology out. So there's always a lot of uncertainty with these things, but it's important to consider these trajectories, because then that's how we know whether we're on track to meet certain climate goals or not. Yeah, so a lot of people trying to figure out what the future is, including myself, but it's a lot trickier than folks think. Okay, why don't we take a quick break here before we dive into the technology a little bit more. Let's come back at 106 and we'll continue forward. And in the meantime, again, if anyone has questions on the lecture or on the homework or on the project, happy to help. Kind of curious, who here has driven or ridden in an electric vehicle, or maybe even a hydrogen vehicle? Anyone?
I have.
Cool.
Yeah, one of my cousins has a Tesla, and I drove it once.
Nice.
Yeah,
Was
it
it
was
fun?
fast. Well, it was at night, and I was on a windy road, and I was so scared.
Yeah. Yeah. Wow. Okay. So there's quite a few people in chat, it seems, as well, who've done it. A couple Model 3s. Yeah. Actually, last year, I've heard this. I should check it before I keep telling people, but I heard that the Model 3 outsold Honda Civics in California, which is crazy. Thank you. Apparently, the Tesla outsold the Honda Accord, but not the Civic. Makes sense. Okay, let's push on. So we've talked about the internal combustion engine vehicle and the sort of workings of it. And so we're going to do likewise for electric vehicles and for fuel cell vehicles. But the nice thing is that actually the system is much simpler, right? And so in terms of the moving parts, there's essentially one moving part in the drivetrain for the electric vehicle, which is your motor. And that's it, right? And so when you think about a gas vehicle, it's enormously more complex uh, and really kind of fascinating if you think about it, right? So in a gas car, you've got your pistons, which moves the crankshaft, which moves the timing belt, which moves your camshaft. All of that is connected through the transmission system, which has many multiple sort of moving gears. And so I think the more sort of moving parts you have, the more susceptible the vehicle is to wear and tear and maintenance issues. And so one of the big benefits of having an electric vehicle is actually way less maintenance. So you don't need to do oil changes. You don't need to change out your timing belt. You don't need to change out all the fluids that you need for the radiator, for example. Um, and actually, also because it does regenerative braking, your brake pads last a lot longer. Although I've also heard that the tires actually wear a little bit faster on electric vehicles. Because typically they're on the regeneration is happening just on the two wheels instead of four wheels, because it's the wheels associated with the motor. So I think that the tires wear a little bit faster. But for the most part, maintenance issues are and costs are much lower for electric vehicles. Okay, so you've got your battery that feeds electricity into the motor, which is the thing that's spinning the wheels. There are a couple other things that are unique components of the electric vehicle, but that's kind of the main guts of it. There is a power electronics controller that controls the power system in the motor and the connection with the battery. You got the converter, which has to do with when you charge the vehicle, it needs to make sure that it converts from alternating current, which is what's available on the grid, into direct current, which is what you need to charge the battery. But yeah, I think pretty overall simple, or quite a bit more simple system than a gas vehicle. Oh, I don't know why this happened. This should be an arrow. This is just kind of describing the battery chemistry. You don't need to memorize this or anything, but essentially the way this works, almost all electric vehicles these days use a lithium-ion battery, which actually describes a whole suite of different batteries. But essentially, you have the movement of lithium ions that go from your anode to your cathode to create electricity, and that electricity is what is powering the motor. Okay, as I was mentioning, so a lithium-ion battery refers to a whole suite of different chemistries. And so you've got things like lithium iron phosphate, lithium ion manganese oxide, lithium nickel manganese cobalt oxide. Again, these aren't things that you necessarily need to remember. But the thing about lithium ion batteries is that these technologies have different characteristics. So we're not going to get into, the mechanical engineering aspects of batteries, but just know that depending on the chemistry of the battery and the configuration of the battery, you have these inherent trade-offs between the weight and density and power output and energy output. And you can see this sort of trade-off happening here. And there are, specific improvements where you can get smaller versus lighter, right? So this dark blue is a lot of where our mainstream lithium ion is today, as opposed to, as I was talking before, those hybrid vehicles that use a lot of nickel metal hydride NMH batteries, and then the old ones, lead acid batteries, which you'll still find in basically every car today. When we say car battery, it's actually referring to, the small lead acid battery. And nickel metal hydride systems have more recently started to transfer to lithium ion, but lithium ion has been sort of the starting point for a lot of electric vehicles. Yeah, here's a little reference point for a AA alkaline, like a Duracell or Energizer battery would be right here. So again, some of these trade-offs, one of the most common characteristic trade-off is between energy versus power density. And this is actually one of the reasons why you don't see like a pickup truck, an electric pickup truck yet, and why we started with smaller vehicles. So it's not as though you couldn't get a pickup a battery to work in a pickup truck, but you also have to remember that, if I compared like a Honda Civic to a Ford F-150, the power output of my Honda Civic in that engine is much smaller than that of the pickup truck. And so as I think about that translating to batteries, I can stick some batteries in. In the Honda Civic example, you wouldn't need so much power coming out of the batteries, which lets you put more energy and get you to the range that you want. The problem with the truck, right, is that it's a lot bigger, requires more power density. And so you could put those batteries that are more tuned to have higher power, but then it would have really low range, right? You're making a trade-off with energy density. It's one of the sort of fundamental trade-offs in battery design. And so to be able to provide the power that the larger vehicle needs, you sacrifice on range, and you think, well, I could just stick more batteries in there and that would improve the energy density, which is true, but then you're also sort of further decreasing the efficiency of the vehicle, because it's getting heavier and heavier with more batteries that you're putting in. It takes a lot of space, and it becomes more expensive. And so I think that's the reason why you sort of inherently see electric vehicles starting sort of small and then getting bigger and bigger. And it's pretty exciting, I think, in the next year or two, although I guess I've actually heard some delays now from some companies like Rivian, which are producing electric pickup trucks. I think over the next couple years, as the technology continues to improve, you're going to see more and more of these larger vehicles becoming electrified. So I think it's kind of just a matter of time as the technology improves and the economics and the cost of the batteries decrease, that we'll see electrification propagating to all classes of vehicles. And so that's a lot of the evolutionary things where you're going in from this end of the circle up to this end of the circle. There are also sort of these revolutionary types of things where we're talking about different sorts of chemistries or battery configurations. So things like lithium metal, zinc air, lithium air batteries. These are batteries that in theory have really good energy and power density and weight and size characteristics. But a lot of these are sort of confined to research and development phase right now. A lot of this is work being done in labs. I can tell you that a lot of these batteries are super promising, and they can do they have pretty crazy characteristics of energy and power density compared to even lithium ion batteries, but they do tend to like explode a lot. So you probably don't want them to be getting put into cars right now until we figure out a way to stabilize them. This is a really famous graph from my field. This is coming from a paper published in Nature Climate Change about the cost of batteries. And so this paper came out, I think, in 2013 or 2014. And basically these researchers went around and they wanted to figure out what the cost of the battery was, because the economics is a pretty pretty important component of the success of this technology, right? Electricity is actually a lot cheaper than gasoline on a per energy basis when we think about electric vehicles. And so the reason, there's a couple different reasons why people are buying gas cars instead of electric cars, but probably one of the biggest ones is simply the cost. They're a lot more expensive, and that has everything to do with the cost of the battery. So this has been well studied. And in 2013, 2014, these researchers got together and they asked a bunch of companies, they asked other researchers, they asked battery manufacturers and car manufacturers, and they elicited a range of prices that were historic over here, and they sort of extrapolated out to the future to see what those battery prices would be. So there's a lot of uncertainty. But I think the one thing that happened before I get there, I should say you'll notice there's red bar here, and that bar is at this number $150 per kilowatt hour. So that's referring to how much it costs per sort of unit of battery capacity, right? So $150 per kilowatt hour is kind of like the widely accepted number that people consider. If battery prices get to that point, then over the lifetime of the vehicle, a gas car is going to be equal to an electric car, right? Because electric cars will be at $150 per kilowatt hour, will be slightly more expensive when you buy it up front, but then they're going to make that money back because you're saving in electricity versus gas. And on average, you should be able to break even at $150. So that's the number that everyone had their sights on. And the big question was, when will electric vehicles get there? Will it be, 10 years from then, 20 years from then, right? Because that informs the economics and when it will make more economic sense to purchase an EV versus a gas car. So no one talks about that number anymore, and the reason why is because this projection fell way faster than any expert predicted. So in 2020, the sort of mean projection was around $300 to $400. But most experts agree that we're already at 150, or we're probably between 150 and 200, depending on who you ask. And so none of the projections I mean, I haven't seen any in any scientific paper that said we were getting to that number before, 2030, 2025, 2030.
And then there's a question.
Yeah, I'll talk about this in a second. Yeah. Yeah, and so as these battery prices have fallen much faster than anyone's expected, I think that's also picked up a lot of momentum in the automaker industry and sort of jumping on board with electrification. So now the new number that most people are talking about is $85 per kilowatt hour instead of 150, and that number represents, if you get down to 85, not only is it going to be cheaper over the lifetime of the vehicle, actually the initial purchase price will now be cheaper than a gas car. And so that's the new number that everyone's looking forward to, and who knows when we'll get there. I'm not even going to pretend to guess because everyone was wrong before, and I'll probably be wrong if I guess. Okay, yeah, so there's a question: how's the race to control lithium reserves affected politics and the economy? Yeah, and so there's this similar political dynamics in Latin America that have existed in the Middle East. Yeah, that's a super interesting, relevant question these days. It's kind of hard to say. I'm not an expert in sort of the political economic situation about the reserves. I know that it's definitely a point of contention, but I think that so from my understanding and exposure to this topic, lithium itself doesn't seem to be the one of the big limiting factors. I mean, it definitely is in consideration, but when we go back to thinking about these chemistries, there are, of course, different reserves and resource availabilities for all of the different chemicals in here. The one that I have understood to be the most problematic is cobalt. And actually, that's because there's basically one place, one sort of mine that dominates the majority of the resource in the world, in Africa, in conflict areas. And so that has been definitely problematic. Yeah, so I would say I can't speak too much about this because I'm not super familiar with the political situation and trade situation regarding of these materials, but I do think it's something that lots of folks are thinking about, and so there's definitely studies and discussions and organizations that have published reports about this. I haven't heard it being characterized as analogous to the situation in the Middle East, but I guess I wouldn't be so surprised if that were to happen. I don't think we're quite at that situation yet, but it's good to have that insight. Okay, great. So I'm going to skip this because we've actually talked about the motor before. Yeah, so this is a diagram analogous to the one before, but instead of a pure electric vehicle, battery electric vehicle, this is a plug-in hybrid electric vehicle. So this one is probably the most complicated because it's got components of everything, right? So it has all the components of your regular gas engine. So you have your engine itself and all the things associated with it, right? The timing bell, crankshaft, camshaft, cams, fuel injectors, the transmission, all of that. But you've also got a battery connected to a motor, the power electronics controller, you've got your converter. So definitely these things are, from a technological standpoint, most complex because they're combining the complexity of the two technologies. you also, right, you also have the downstream exhaust system, which you don't need in a battery electric vehicle because there are literally no byproducts. It's just everything's contained within the battery. To further confuse you, the plug-in hybrids can be designed in a slightly different configurations, and different vehicles that exist today are in a lot of these different configurations. And actually, even when you talk to folks at like dealerships or something, they don't know anything about this. Actually, to go on a bit of a tangent here, the one of the big things with adoption of electric vehicles that we study is again with consumer behavior, and one of the issues that we studied in the past is looking at how dealerships are promoting these new technologies, and a lot of times they don't really know how to deal with them. They discourage consumers actually even from buying electric vehicles. It really depends on a case-by-case basis. But anyways, going back to this, okay, what's going on here? So in a series configuration, your engine cannot actually turn the wheels of your vehicle. So what happens is you've got it's essentially a gasoline generator. Okay, so it is it's like a lot of the generators that we've talked about in power plants, where you're doing combustion to spin something, and it's spinning the generator to produce electricity for the battery, and all the electricity in the battery can then go into a motor that spins the wheels. So in a series, only the battery is able to spin the wheels, and if you have your engine on, the engine is powering the battery directly and not the wheels. In a parallel plug-in hybrid configuration, either the engine or the battery through the motor can operate the drivetrain. And so you're kind of switching between the two. And then in a series parallel, your engine is going to a generator, and that generator can operate through a transmission system to power the motor and spin the wheels, or the generator can provide electricity to the battery, and the battery itself obviously will be able to power the motor and spin the wheels. And there are different reasons why you would want to do these different configurations, having to do with efficiency and costs, and you know, how much you're relying on the engine versus just the battery, right? So like a series PHEV, for example, you probably don't want to be using the engine a lot. It's mainly kind of a backup, and so an example of this might be something like the BMW i3 has I believe has a series based plug-in hybrid system, where it's really just kind of a gasoline backup. Yeah, and so even in the series parallel hybrid case, there are a couple sort of more complex configurations, which we won't talk about. But just so you know, plug-in hybrids themselves can be pretty complicated. So if one were to ask you, hey, like, when you do a plug-in hybrid, do you operate just on the battery or just on the engine, or a combination of both, or can you switch one off and just use one? Yeah, it depends. It depends a lot on the exact vehicle that you're driving, because they're going to have lots of these different configurations. When we talk about adoption of the technology, I think there's a common one that people point to as a drawback for electric vehicles, which is um, the time that it takes to refuel your vehicle. Uh, and so when we think about a conventional vehicle, okay, you drive up to a gas station, you fill up in a couple minutes, and then you're good to go for another 300 miles. Whereas with an electric vehicle, it can take some time to charge, quite a bit longer, actually. Um, but actually, I like to point out that, one of the, with the flexibility of charging, it can actually be a pretty big benefit. And so when I ask people, who actually enjoys going to a gas station, right? Very, very few people say that they actually like going to a gas station. And so the benefit of an electric vehicle is that you don't have to. You can refuel at places that you normally go to, right? So you go at your home or at your workplace, or in public areas where you're going anyways. If you're going grocery shopping at Whole Foods, for example, you don't need to take trips that are unnecessary to refuel your vehicle. And sure, it definitely takes a lot longer to fuel up the car. On the other hand, um, your car is spent parked the vast majority of time, right? 22 to 23 hours of the day, your car is just sitting there. So does it really matter that you that the charging takes a lot longer, as long as you have access to it? Yeah, probably not. But it's still a perception issue, and it is still a real thing where the charging takes quite a bit longer. So I'm not going to sort of discount that, but I will point out that there are some benefits to being able to be flexible in where you're recharging the vehicle. Charging itself is a little bit complicated and confusing. So these days we talk about different types of charging. When it comes to electric vehicle, you've got level 1, you got level 2, and then you have DC fast. So the charge port for level 1 and level 2 looks like this on the left, although that's in North America. In Europe, they actually use a slightly different connection device. So J1772 is the standard in North America. So all electric vehicles can do level 1 and level 2. Not all can do DC fast charging. And that division is usually the plug-in hybrids versus the battery electric vehicles. So battery electric vehicles, since they have a bigger battery, are the ones that do DC, that have the capability of doing DC fast charging. So level 1 is up to 1.1 kilowatts. That's about charging of 5 to 6 miles every hour. So if you needed to charge, say like 100-mile battery, and you plugged it in with a level 1, it would take basically the whole day, right? Maybe 20 hours or so. The level 1 is just a regular outlet. So you could just plug this into any old outlet, and you'd be getting something like a kilowatt into your vehicle. Level 2 is higher power. It's in theory up to 20 kilowatts, but there aren't really any AC systems that are running at 20 kilowatts to input into your car. So the vast majority of level 2 is going to be either in 6.6, or 7.2 kilowatts. Okay, so this is this would be equivalent to the amperage from like your dryer plug. If you've ever plugged in a dryer before, you'll notice the plug is really big and a little bit different. It draws a lot more power. So this is sort of rated at an equivalent sort of output. And at 6 kilowatts, you're talking about something like 25 to 30 miles per hour. So if you had a 100-mile charge, then you could get that in maybe 4 or 5 hours. I should also mention that the charging isn't like with gasoline, where you just where you fill it up and it just dispenses gasoline at a uniform pace. Your battery will actually change voltage as it's charging up, which makes it harder to push the electricity into the battery, essentially. And so it will slow down as you charge your vehicle more and more. So you could go from 0% to 80% in X amount of time, and then it would take another X amount of time to go from 80% to 100%. So the first 80% is about, that's roughly what we say is about the same amount of time as it goes to go from 0 to 80 to go from 80 to 100. Okay, and then now we've got our DC fast chargers. There are 3 basic standards for DC fast charging. You've got CHAdeMO, you got CCS, which is I'm totally blanking on the acronym. It's combo. It's a combo charger. And then the last one is the Tesla supercharger, and those only work on Teslas. So these aren't just kind of like interchangeable nozzles. Like you can't just have an adapter head for a different one and plug it in. There's actually a lot of like power controllers and power systems that are particular to the way that they dispense power through these and through the controllers in your vehicles. So they're really not compatible with each other. So DC fast charging can go anywhere from 50 up to 400 kilowatts. So level 1, level 2 are an AC power. DC power, direct current, you can get a lot more in. But the vast majority today of DC fast charging is 50 kilowatts. And Tesla superchargers, which run at 120 to 150. New vehicles, new non-Tesla vehicles, full battery vehicles being sold today are starting to go up to 100 kilowatts, 100 to 120 kilowatts. So they'll be able to charge twice as fast. And that's kind of this gradual development. So that at 50 kilowatts, you're talking about within an hour, you can get anywhere between 150 to 300 miles per hour if you're doing 120 kilowatts. Yeah, and so quite a bit faster, but still sort of taking a little bit of time, but it's something, for example, in Davis, there is a DC fast charger where the Whole Foods used to be, and you could, in theory, plug in at a DC fast charger, go in, grocery shop for like half an hour, come back out, and your car would have filled up, something like 75, 80, maybe 90 miles. And so these things exist to help top off, but also on longer trips, if I'm driving all the way from Davis down to Los Angeles, for example, you could stop somewhere for lunch to fill up fill up your vehicle sort of halfway through. You might have to wait a little bit longer if you wanted to fill it all the way up. But DC fast chargers are trying to speed up the charging process. So I actually drive an electric vehicle, and my wife has one as well. And one of the annoying things is that there are a lot of providers. And so these are different vendors, and so they'll follow all the same standards. They'll have your J1772 chargers, And they'll have either CHAdeMO or CCS, or if you're Tesla, they'll have the Tesla superchargers, and they're all over the place. Some of the really big ones, ChargePoint. I'm sure you've seen this before, like at Target in Davis, they've got a bunch of ChargePoint chargers. EVgo is a really big one for DC fast charging. Blink, that's a yeah, I mean, there's a lot of these chargers around. They recovered them from older chargers and sort of rebranded. That the ones at IKEA in West Sac are Blink chargers. So the kind of annoying thing about this is that unlike a gas station where you just kind of pay with a credit card, a lot of these are sort of specific to the provider, and so sometimes you might need a membership, or oftentimes you're paying through an app. So if I open my phone, I have like 17 different like charging provider apps. If I go to a specific location, I have to find the one and sort of match to the provider to be able to use it. Yeah, okay, there's a good question here. How does the charging fee vary between the different levels? Or does it matter only with the amount of energy instead of the speed? Yeah, that's a great question. So I'll talk about the technical answer, which is, so strictly speaking, if you're buying electricity, you're not allowed to get charged more than what the PUC allows for. So last class we actually talked about in the electricity grid how electricity rates are determined, and that has to do with this big regulatory process through the Public Utilities Commission, and they basically say you are not allowed to charge more than this amount for electricity. So in theory, you should be paying by the amount of energy that you get, but that is not how this works with the providers. So first of all, you will have no idea what you're paying a lot of the time as you go from provider to provider, or even within a provider. So like ChargePoint, for example, they sell the equipment to the vendor on site, and then the vendor can charge whatever they want. So Target, for example, it's free for ChargePoint for first couple hours. But if you go to another location, say I were to go to the California Energy Commission, they got a parking lot over there, and then if you park in the parking lot, you get charged some amount of money right from the get-go. So even within ChargePoint, it might be different. For a company like EVgo, they actually own all the chargers, and then they will charge some amount of money. Either you get a discount if you're a member and you pay like a monthly fee, or you pay some flat amount per amount of energy. But the amount that you pay for the energy can be actually a lot higher than like retail rates. So if I were to charge at EVgo, I would probably be paying maybe 35 cents per kilowatt hour, whereas the retail rate, so what you pay for electricity at home, is maybe 17 cents to 21 cents per kilowatt hour. So maybe half of what you would pay if you were to charge your vehicle EVgo. And so if you've been paying attention to what I've been saying, you might think to yourself, wait a second, you just said that you're not allowed to pay more for the electricity. So the way they get around this is that they're not charging you for the electricity. They're essentially charging you for like the parking space, right? They're not saying that you're paying for the electricity, you're paying for other sorts of services associated with it. And so you can get around this issue of just electricity. So in terms of what you pay, it's super duper confusing and not altogether straightforward, because sometimes you pay by the energy, sometimes you pay by how long you're there, sometimes you pay by the power going in, and sometimes it's just like a flat rate. And a lot of it's confusing because Also, if you're paying by time or if you're paying a flat rate, if I sat there for half an hour when my battery was completely empty, I'm going to get a different amount of energy than if I sat there for half an hour when my battery was at 80%, right? Because it charges slower when the more full your battery is. Yeah, so super complicated, not straightforward. I wish that actually they had a system. They have this nice system in Norway where basically the government forced all of the companies that provided charging, all of these providers to have this like standard RFID membership code, and then they would hand them out to people who bought uh, electric vehicles. And so when you get an electric vehicle in Norway, you can apply to get this like key fob, and that fob can activate any charger in the country, as opposed to you having to download a specific app and use that to unlock the charger to charge your vehicle. Hopefully California will do that one day. But I don't know, maybe it's too late. Yeah, because there's already a lot of chargers out there. In California, we have maybe something like 20 to 30,000 chargers available publicly. So that's not even counting chargers at home. There's a lot more, I think, than people think, and actually this map is already getting pretty old. I need to update this one as well. Yeah, the network of electric vehicle chargers is quite large, even if you don't sort of notice it directly. Okay, so I talked about level 1 and level 2 and DC fast, and there's a new breed of chargers that are being developed called extreme fast chargers. And so these ones are starting at 350 kilowatts and upwards. So DC fast is 50, the Tesla superchargers at 100, 120. Even the newest ones are going to be at maybe 150. These guys are crazy. These are 350 kilowatt chargers. And the whole idea, right, is that one of the perceived drawbacks of electric vehicles is the limitations in range and refueling. And so the whole idea behind an extreme fast charger is to replicate gas stations. Again, I'm not necessarily I don't necessarily think that this is a good thing to pursue, or that people necessarily want this, right? As I was mentioning, no one really likes going to gas stations. And so if I had the ability to go to a gas station versus just have it slowly refill at home, I might prefer that. But nevertheless, there are others with differing opinions about this, and this could be really useful for something like if you're doing like a long distance trip to from like NorCal to SoCal, for example. And so these these chargers can charge a full 300-mile battery in maybe 10 minutes or so. They're extremely high power, pretty dangerous actually, 350 kilowatts. The cables themselves actually need to be liquid cooled. There is one, or maybe there was another one that was installed recently, but there's definitely one station that has 350 kilowatt chargers that was installed early 2019, so like a year ago, in the Bay Area. And so these chargers are not just in theory; they're being deployed in reality even today. That having been said, these chargers, no car can charge at 350 kilowatts. And so this is kind of putting the technology out a little bit early. There are no existing commercial technology that could actually handle charging at this rate yet. The first vehicle that will be able to do a form of extreme fast charging is the Porsche, um, the new Porsche that's coming out, which is going to be able to charge at 200 kilowatts. So not quite 350, still really, really fast. But again, eventually I think, in my opinion, I think it's going to be only high-end luxury vehicles, expensive vehicles that will be able to go at these speeds. But we'll see. Okay, I went way slower than I was expecting today, so we'll probably have to hold off on hydrogen and talk about that next time. But we'll end today thinking about a tie-in to last class's lecture, where we talked about the electricity grid. So here's where, this is actually one of the main subjects of my research. What happens when you actually plug in the vehicle? Oh, okay, so I see a question. If no one can charge with those 350 kilowatt chargers, why create them already in the Bay Area? Yeah, good question. I mean, it's kind of like a chicken and egg thing, right? So like if we were to produce vehicles that could do 350 kilowatts, and there weren't any chargers, well, then we would say, why did we make these cars if we can't charge them at that rate, right? So something has to come first. It just happens to be the chargers. Probably makes sense that they're first because it's probably easier to make the charger than it is to make the car. But it's not like they're like being widespread deployed. There's literally one station with a couple 350 kilowatt chargers. And it's probably good that they're doing that anyways, because they're going to be able to run tests. They're going to be able to look at the durability of the chargers and all of that sort of stuff. So I wouldn't say it's completely wasted that they've developed them. And actually, they can they can throttle the chargers. So you could take a vehicle that's compatible with a DC fast charger and plug it in, and it would run just fine at a 350. And I'm pretty sure that's what they're doing now with those chargers. They just charge the vehicles at 50 kilowatts instead of 350 kilowatts. Yeah, and I see another question. Is there any damage to the car if charging becomes too quick? Yes, definitely. And that's one of the reasons why the technology hasn't been developed yet, or hasn't been rolled out commercially yet. So one of the fundamental properties of a battery is degradation. And so you guys all have smartphones and iPhones and Androids and whatnot. And you'll probably notice that after a couple years, the battery starts to degrade. I mean, it doesn't last as long, right? And eventually you go and get yourself a new phone. And the way that a battery degrades is, so one of them is cycling. So if you go from a full battery to an empty battery, up to a full battery, down to an empty battery, batteries are meant to last a certain number of cycles, and they will degrade in their capacity over time as you go through those cycles. One of the ways that you can make that degradation accelerate is if you change the rate at which the cycling happens. So if it's a lot faster, it's going to operate at a higher temperature, which accelerates the degradation. And so one of the challenges that they're dealing with DC fast charging is exactly this issue, is the temperature. So the batteries will get really hot as you charge them really quickly. So even the Nissan Leaf that I drive, I cannot charge it up at 50 kilowatts and then drive it for the full range of the battery and then charge it again at 50 kilowatts. So you can't charge the battery all the way up, drive the full range, and then charge it with a DC fast charger. because the temperature will get too hot. And the last generation of Nissan Leafs was one of the last. It was one, yeah, I think it's the last full battery electric vehicle that had a passive cooling system, which means that it didn't have like liquid cooling or like a fan that would blow air to cool the battery. It was just airflow from the movement of the vehicle itself to cool it. Whereas basically every other battery electric vehicle has an active cooling system. So basically, if you are constantly fast charging it all the time, or if you're doing this crazy 350 kilowatt charging event, you are likely degrading your battery faster. So it's probably not really noticeable at all if you're just doing it occasionally. And if you're doing the 350 kilowatt, even at that, if you're doing it a couple times a year, it's probably not going to do anything to your battery. But if you're always charging with that, you're probably going to degrade the battery a lot faster. Okay. So there is this concept called smart charging, which actually a lot of people, even in the research community, don't really they don't really know what it means. They basically say, oh, smart charging means that you are like reducing emissions when you're charging. But in and of itself, it's actually a fairly not straightforward topic. Okay, so this is an example of like different times of the day over a course of a day. When would be the ideal time to charge to reduce emissions? And so this actually requires a whole lot of work where you're figuring out, what power plants are turning on and off at different times of the day. And if you were to charge your vehicle at a specific hour, what power plant is turning on and off to respond to that. And so not only do you have to know what the load is from the electric vehicle, you have to know the load from everything else to figure out what power plants are responding based off of the dispatch curve, which we talked about last time. And so this is just an example I'm showing that it can be pretty complicated, because you could say, oh, smart charging, you should charge between these hours, right? But if you're in New York on the left, for example, versus if you're in Los Angeles, it's actually almost the complete opposite. In New York, you'd want to be charging in the middle of the night, but in Los Angeles, you'd want to be charging in the middle of the day. And so this is actually a really big field where we're talking about the interaction between the vehicle and the grid. So there's what we call V1G, which is unidirectional. And so that's where the utility or your system operator has some kind of communication protocol with like a smart building or a charging station. And then it'll say if your vehicle is plugged in, it won't necessarily charge until it's given a signal to do so. And that is one form of smart charging, where it says, essentially it's something like, hey, wait until there's a lot of like solar power being provided, or maybe we have excess energy, or maybe wait until electricity is really cheap and then charge your vehicle. The sort of more the next step, which isn't something that really exists on a commercial scale yet, is called vehicle to grid. So V2G, and this is bidirectional. So it's got the similar type of thing, but maybe it'll say, hey, you've got this battery in your car that can store electricity. So let's buy electricity, or in other words, let's charge the vehicle when electricity is really cheap, and then let's sell the electricity when the prices go up. And so you could actually, or conversely, let's charge the vehicle when emissions are really low, and then let's discharge the vehicle when emissions would be really high. In other words, you're displacing a power plant from turning on by providing electricity through the battery on your vehicle. And so this system in itself, there's a lot of sort of nuance here. everywhere from the technical perspective of how you would actually do it, how you would operate the battery, to this economic level of like how you would do price signaling, all the way to sort of the more social level about how you change people's behavior to allow for this. What would the costs need to be in order to get people to participate in a program like this? And so there's many different layers that you could research and study in this area. Yeah, ranging from technical to economic to social and individual behavior. Again, this is a pretty big field, and I think that there's potentially a lot of value that hasn't been captured yet, right? Because this isn't a thing that exists in the current day. Great. Okay, so why don't we end here for today? The next set of slides is kind of moving us on to hydrogen vehicles. So we'll finish that up next class before we start to dive into energy policies that are related to basically all the technology and economics topics that we've talked about thus far. Great, so we'll end here, and I'll stick around a couple minutes if there's any questions.